Good day everyone, I am Frederic Salimi. This e-course will be uploaded in our training workspace. If you are interested in full access of this e-course, please send us an email given in description. Have a good day and talk to you later. A brief description about my qualification and experience. I have a master's degree in dependability, which covers safety, reliability, maintainability, and availability. I also have a BS degree in process control and instrumentation. I worked several years with engineering companies like Technip and operators like Total. I was involved in pre-project, FEED, detailed design, construction, and operation. Today we discuss about consequence analysis. We discuss about modelization for fire, explosion, flammable, and toxic cloud dispersion. This is a generic version and will be customized for your project or for your installations later. This course takes 1 day. We give you access to EPC 365 training monitor for discussions. The objective of this course is to give a practical understanding of consequence analysis, fire, explosion, flammable, and toxic cloud dispersion for oil and gas installations. So if you remember from the chassis management system, I discussed about the identifications of the hazards and assessment of the risk. And for this, there were certain techniques for, we call it scenario-based risk assessment. We call them detailed risk assessment, DRA. And from DRA, we have to understand the scenario of the risk. And then based on that, we will define the strategy. Now, the consequence analysis framework, I want to show you how it works. We do hazard identification by HAZID and HAZOP, and then we do the DRA, which we identify the scenario of the risk, and then we do the modelization for the dispersion for flammable and toxic gas cloud, fire and explosion and oil spill, and finally we see the domino effects. I'll show you first how to download ALOHA and work with it, and then we discuss about the theory behind all of these modelizations and the limitations of ALOHA and how you can use it for particularly for pool fire and jet fire. You can download ALOHA software from the EPA website. And it is a very good package for understanding consequence analysis and emergency response. So let's start. I show you the ALOHA software. Basically, when you enter in ALOHA, you can insert the location. You can add a new location. And also you can, if there is an accident, you can set the date and time, and then you can simulate and write the lesson learned from that one. For the setup, you can choose the chemical for, it has the pure chemical and solution. I choose for easy understanding methane. If you click by M, you can come here methane, and then you go for atmospheric input data. I put the wind decibel of 2 meters per second, and it comes from the south. We can change the direction, and then later in Marble we can see the direction how it goes. There is a help in all the item that it helps you what to write and understand the input data. And then when you put the atmospheric data, then you can put the I put it here, a tank with diameter 3 meters and the length 5 meters, and then
This is a package. It's a tank with gas, only methane. Tank pressure is 20 bar. And then I want to calculate a leaking tank. Chemical knot is burning. I want to see the LEL, how far it goes. You can also see the jet fire if you want. Here I put a 2-inch diameter hole, and it gives me about 120 meter distances that my LEL, 10% of LEL goes. So 10% of LEL goes to 180, and 60% of LEL goes up to the this area, which is about 50 meter or something like that. So in order to see it in the layout, when you go to pool, you can see here. And if I put it here, you can get this information from the Google Earth, or the Google satellite, or other sources that you can see here. So one of the things which is important here, for example, if you click here, you can by right hand side, you can see, for example, the information about here, because this is very important. If, for example, if it was H2S, the operator can see, for example, these people should stay at home, or these people evacuate, and they can give the information about the situation. So, but here, for example, if I go to ALOHA, and I change the wind direction, atmospheric, and I put it from east. I put it like this. It will change the direction. So if I go to sharing Marple, and if you see, it goes that way. So near you see here, for example, this is very important for the toxicity, but also for the because your project has already done the DRA, and there are different scenarios. You know what will be the impact, but here you can see the LEL goes up to this building, and you can get the necessary measures for the simulation drills, and also informing people about the accidents.
You can work with ALOHA for modelizations of the pool fire. You can model a propane pool fire, diameter of a pool 10 meter, wind speed 5 meter per second, and temperature 25 degree with a confined fire, and flame height of 21 meter, combustion rate to 400 kilogram per minute. When you do this modelization, we discuss in our workshop about your questions and the input data. The same things here, result for methane tank. Diameter of the tank 20 meter, height is 20 meter, temperature 25 degrees C, and atmospheric condition is stability class D and wind speed 5, and a 2-inch hole on the tank shell at ground level. Burning unconfined pool with ALOHA. So you do this, you will achieve or pool, calculate for you the pool diameter 27 meter, flame length is 11 meter, and this is the results. You can also do the firewall and BLEVE, boiling liquid expanding vapor explosion, which is a rapid release and ignition of flammable under pressure at temperature higher than its normal boiling point. And the main consequence is thermal radiation, and you have a secondary one, a flammable missile over pressure, and BLEVE. And with Xplo CFD, we will show you how you can see the overpressure for secondary consequences. So for the fireball and BLEVE, we can say very rapid phenomena, expanding velocity 10 meters per second. Limited duration is very short duration, about 30 seconds, even for a very large tank. And significant extent of fireball radius in the order of 300 meters for a very, very big tank, 4,000 cubic meter, and very high emission power. Is about 200, 350 kilowatt per square meter, and no precise capability for prediction of when it will happen. Usually initial step for tanks exposed to heat, pool fire, jet fire, or opening of the PSVs. So you can model this with ALOHA, and you can take and you can see here it will give you the how many kilometers. For example, it's about 700 kilometers for the 3 kilowatt per square meter, or 6 or 15. You can the possibility in ALOHA to change these limits and understand based on the criteria that you have, and you can calculate them. The same things here. It is for 1,000 cubic meter propane tank. There is an exercise like this. You do it, and you will prepare yourself with your questions in our EPC 365 training workspace, or in our workshop. We discuss about this. So jet flame is ignition of gas or two-phase release from pressure vessel, and this is a propane jet flame test, and mainly thermal radiation. ALOHA is very good for that. You can use jet fire for this. There are other packages that you do like FAST. This is for professional, and you do it for the DRA. But if you have an accident, and you can use this to understand for the lesson learned. So jet flame characteristic is a result of outcome of gas or two-phase release of flammable substances. It has a cone shape. Long duration normally depends on source of isolation. Very high emission power, 200 kilowatt per square meter, and suit expected but not affecting radiation level. But this is for normally for the design. Certain project they take it as a 300 kilowatt per square meter for jet fire and 200 for pool fire. But this is something that is from literature. So you can also simulate a 2-inch hole in the top of propane tank, gas filled vertical jet, and you get this result. You have to prepare this. And you see the distances here. For the 15 kilowatt per square meter is about here goes about 36 meter, and you can simulate this with ALOHA and get familiar with this. So the tricky one is vapor cloud dispersion, and I will show you here a couple of theory behind it. And for us is if ALOHA can do the vapor cloud dispersion and explosion, but I think CFD modeling like Xplo CFD, if you can do it, is much more precise. So here is source of a spill here, and if it goes, it will be dispersed, and we go for a downwind and concentration and crosswind. So this is, for example, here the concentration. If you see by distance, it reduces, and here is LPG dispersion, and this is if you see here is You can see concentration is downwind isoplate at ground level, like this is LEL, and etc. So you can do it at ground level, and you can see downwind distance and the crosswind distance. You can see here a different level of the LFL. So pressure cloud dispersion, release condition affecting dispersion, substance properties, boiling point, pressure, temperature at containment, release rate and area, release point, and release direction, upward, PSV, horizontal. So there are a lot of parameters affect the result, meteorological condition, atmospheric class from A to F, wind speed, air temperature, humidity, and type of area, if it is rural, industrial, urban, roughness factor. So here about atmospheric stability, expression of turbulent mixing in atmosphere, related with atmospheric vertical temperature gradient, dT over dz. If you have temperature here, here is with the height is unstable, drier, adiabatic, and lapse rate and stable, and these are the curves from the modelization. Atmospheric stability, if there is unstable, if there is sunshine, strong heating, much turbulent mixing like this, and natural strong wind, and stable weak winds. Normally a strong wind may be associated with F stability. Atmospheric stability usually attributed to a standard class A to F, Pascal class, and class A is unstable, and in combination with high winds favors dispersion. D is neutral, and F is stable, minimum mixing in atmosphere. You see a stability class, for example, this is for A and B, goes like this. Stability class D goes like this, and this is for class E and F. So here you can see the different class of stability. For example, here, if your wind speed is less than 2 meters, you can see here the incoming solar radiation, if it or night cloud cover, gives the different stability class. You should know that for ALOHA or speed, low speed, it cannot modelize well, so you have to be careful with ALOHA. And also wind speed. For example, this wind speed and with the elevation, if you see here, is like this. Wind speed referred in meteorological data usually refer to measurement 9 or 10 meter height. So this is the simplified function, and this P is a function of stability class and surface roughness. So, and also typical set under interest in safety report is D5, stability class D, and wind speed is 5 meters per second, unstable condition. And F2 is a worst case, is 2 meters per second. Especially in heavy gas dispersion, worst case for extent of vapor cloud. And also vapor cloud dispersion is a type of surrounding rural, industrial, and urban. And here, for example, is a trend classification, trend description, and this surface roughness. So you can, the model asks you for the surface roughness. And conservative approach is open country rural. The
very important factor is averaging time. The averaging time is variation in time due to turbulence, but like this, or wind current, speed, direction. And for a continuous release, you see here, it depends. Concentration at constant location is not constant. The concentration can change. And if you see here, increase of the averaging time, Plume boundaries widths, for example, here 1 over averaging boundary. This is 10 minutes. This is instantaneous, and concentration distribution for lattice. And here, if you see 1 over average distribution, it goes like this. And this is for instantaneous. And if you see the relative concentration, you know how it works, and the plume will be changed about the widths and distances, and it has an effect on decision for safety. So very important to use averaging time in models suitable to exposure time under interest. Models may be used parameter for certain averaging time, which might not be suitable for the application in safety. You have to check it always. And Gaussian model uses implicit 10-minute averaging time. So averaging time normally for toxic exposure, usually under interest for a period of 30 minutes. Due to LC50, 30 minutes in endpoint. And ALOHA Degadis is for the heavy gas dispersion, uses 5 minutes for toxic. And ignition of flammable cloud in related with very low exposure time, time just for ignition to happen. And ALOHA Degadis uses 10 seconds for flammable, especially LPG, no matter if toxic effect is examined. And reason for reporting of LFL and half of LFL in flammable dispersion. So we use half of LEL. The reason is averaging time. And 1/2 of LFL reporting contributes to uncertainty of averaging time conservative approach. So if you see here is if we take averaging time 30 minutes or 1 second, you see the cloud will change. This is for propellant release from liquid phase piping. Now, passive and neutral dispersion, Gaussian dispersion here is release of gas with density equal or higher than air. So this you can see it from the hazardous area schedule. If the line, if it has a density equal or higher than air. And passive neutral dispersion Gaussian is release of gas with density equal or higher than air. And basic characteristic is maximum concentration at center line, concentration reducing with increased distance from the source. If released at ground level, maximum concentration at ground level. With ALOHA, you can do the dispersion calculation. For example, an example for dispersion of ammonia, release of 2-inch in hole in 6-bar gas vessel, and stability class D and 5. It goes about 350 meter for if you see here for IDLH. So you should calculate this with ALOHA, and we will discuss it about it later. So passive neutral dispersion Gaussian is equation for point stationary source, no momentum. but jet of the release have significant momentum due to high velocity modification needed in model to take into account release momentum. For jet of release modification are needed, typically example Plume rise parameter to modify the release source point at downstream. So here this is the original, and it is a modification that we do for this. For flue gas dispersion, for example, pool fire combustion product like SO2, a special characteristic, for example, large area of the source, tank area, bond area, not point source modification are available to model for source are treated as 0.1. High temperature of flue gases and the relevant Plume rise equation provided for stacks provide uncertainty from Plume rise height. Conservative approach is no plume rise and dispersion begin from flame end, and especially as atmospheric condition to be considered temperature inversion conditions, and trapped plume is something like this. So this is Plume rise effect, concentration of center line not continuously decreasing with the wind speed, maximum concentration at center line. And this is the continuous release and wind speed, and this is the way that this is Plume rise effect. Plume rise effect also example is for SO2 dispersion and from dike fire of heating oil tank D5, and this is the release rate, dike equivalent diameter 66 meter. This becomes something like this. You know, you do the modelization, and we discuss about it in our workshop. And heavy gas dispersion. So for heavy gas, we should do the CFD modeling, and the ground Plume model continuous release, maximum concentration expected, concentration decreases with increasing distance, more extended Plume expanded to neutral dispersion, meteorological data F2, stability class F, wind speed 2 produce more extended cloud, and propane butane cases, some release sources same hole sizes will produce more extended cloud for propane due to higher release rate. So heavy gas dispersion, and you can do example is release of propane release with a 2-inch hole in liquid phase of tank, and stability class D and speed 5 with ALOHA, and you can see here that the LEL, 60% of the LEL goes up to the 170 meter. And the same things, you can propane release 2-inch liquid gas phase from in the Pascal class F and 2. And if you see here, it goes much more further for the 60% of the LEL. So this is the worst case. So vapor cloud explosion is normally a delayed ignition of flammable vapor cloud under partial confinement. Obstacle with clouds producing overpressure during front propagation, and main consequences of overpressure and the broken glasses. Vapor cloud explosion characteristic is very short duration, less than 1 second, and the model has a high uncertainty through to several assumptions used in every model. And there are different types of model: TNT blast charges, airfoil charges, and multi-energy, CFD, Xplo CFD. And normally one of the recommendation of the HSE in UK is to perform several models and to get the worst case. but normally we don't use these TNT blast charge in my experience in different oil and gas installation. Multi-energy, yes, but I highly recommend CFD, Xplo CFD, which is very easy to use, and you can import your plot plan and see the effect of the congestion for the modelizations of the explosion. The TNT equivalent model is we use this formula, and normally there is a high uncertainty in both alpha E value and quantity of flammables. So as I said, we don't use it in oil and gas modelization normally, but review on topics is in TNO Yellow Book and AICAC CCPS guideline. And TNT equivalency model, this alpha must be selected along the suitable flammable mass, and there is, I don't recommend to use this for the studies, and if you want to do TNT mass, double the gas mass in confined area. So this is the equivalency and the peak release. TNO multi-energy model, something like this. Partial exploration from confined area expected. And energy release assuming stoichiometric combustion based on the air contained in the area, taking into account average 3.5 mg over cubic meter of air for most hydrocarbons. Uniform concentration of flammable in the confined area assumed. So these are the overpressure from Bragg, and this combustible energy and such distance from explosion, and here blast strength 10, detonation explosive case, and not valid for BCE, as propagation of blast via detonation require higher homogeneity in the cloud. So there are certain limitations of this, and we will explain it in another video by Xplo CFD, and also Baker straw tank model. Also, I will say that gas type reactivity, susceptibility to flame from acceleration, taking also into account with obstacle density, methane, CO, low reactivity, hydrogen, acetylene, and high reactivity, and other substances medium. So this takes into consideration flame speed defined by table of gas reactivity here, gas reactivity and confinement type, for example, the dimension, and this is this model like this, and finally overpressure graph using such distance from flammable speed. In the ALOHA, you can use the vapor cloud. For example, you can use a 2-inch hole in a liquid phase tank, D5, and you can use Baker straw tag methods. Here I wanted to say, and even in the package there is a notice at the beginning that the ALOHA has the limitation, very low wind speed, very stable atmospheric condition, wind shift and steering effect, and concentration patchiness, particularly near to the source. The model does not incorporate the effect of chemical reactions, particulate and chemical mixtures, and terrain and hazardous fragments. And you know, the For the simulation, you have detailed QRA, and for the detailed QRA, consultant did it with fast and other sophisticated software, taking into consideration the mixture, and that is for simulation. ALOHA is very good for if there is something happened at site for the fire and explosion, you can do the simulation and you put it on your lesson learned and to see how it works. But you have to know there are certain limitations. Here in this e-course we added a presentation of Dr. Mathad Adel Jawad, and he will explain how the Xplo CFD works and what are the principles of operation, basically taking into consideration the congestion for the dispersion and the explosion. This e-course will be uploaded in EPC 365 training workspace. You can click on consequence analysis, and then when you are in consequence analysis, you can upload all your documentation about risk assessment, DRA, QRA, and other studies that you've done. We will create a e-course, and when it is approved by you, we put it in the FERA community for discussion. So and as you see here, can be used ALOHA for emergency response. As I said, that ALOHA is very good for pool fire and jet fire, but for the dispersion and the explosion, other packages like Xplo CFD is much more appropriate, taking into consideration of obstacles. Thank you very much for your attention. If you have any question, please send us an email at pmc@epc365.com. We have two websites in French and in English, which explain very well our approach for consequence analysis. And if you have any questions, there is a request form, and you can send us an email, and we will get back to you as soon as possible. Have a good day, and see you in our next workshop.
Hello and welcome to an overview of Xplo CFD version 7. This is the latest version released in 2020 amid the COVID-19 crisis. We're going to go through just basically how the software operates, so as to give you an overview of how things work. And it's still basically the same mode of operation. The way that the software works is basically you read in a PDF of a plot plan or an offshore platform or an FPSO, what have you. Usually it's a top view, but it can be a side view, and sometimes those are very useful. You can select the domain to be either the entire plot plan or part of it by controlling things, and then when you're ready to go, you can set it to run, and the way that it runs basically is it's a hybrid code. So the code will first analytically estimate the source terms. So if you're doing a gas explosion, it uses CSC, the confinement specific correlation, which has been proven to be far more accurate than the multi-energy method, because it's able to decouple confinement from congestion. It also does BLEVEs. It uses the method by Plume from 1991. Basically, he's converting that into a TNT equivalent explosion. You could do a TNT equivalent explosion if you're doing something like ammonium nitrate or an improvised explosive device like a terrorist activity. So you calculate the source, the strength of the explosion, that is then passed on to SU2 or open source CFD software, and that allows you to propagate the explosion into the wider domain, and we'll show you exactly how that works for several examples. It's run in a 2D fashion. This is deliberate because SU2 runs in a 3D way, so you can configure SU2 to run on detailed 3D geometries. There's no need for that, and in fact, CFD softwares have traditionally been for explosions. All of the CFD softwares have been traditionally dissipative. And so to not be on the under-conservative side, SU2 is configured in a 2D simulation. So you're basically solving at the ground level. And then the output is visualized with PowerView, very powerful visualizing tool that shows you exactly how your explosion is interacting with the rest of the domain. Let's talk about gas explosions. In the past, to do a gas explosion using CFD, you basically had to model the site in 3 dimensions. That's expensive, it's time-consuming, it may not always be possible, and in fact, the end result of 3D CFD used for explosions has a large uncertainty. And this is something that we don't discuss too often, but there's a 30-50%, even order of magnitude sometimes, uncertainty for the state-of-the-art CFD. So it pays to be conservative and to try and stay within the sort of limits or the uncertainties of 3D CFD. And that's the approach that we've taken to actually model this. So instead of doing all of that, software now relies on just the plot plan and simplifies things and stays within the uncertainty. We'll get to that in a minute. But if you were to, as bad as CFD is in terms of uncertainty, apart from CSC, the multi-energy method, for example, is even worse. And in fact, we have a paper from 2010, I believe it might be 2014, where we looked at a comparison of the gain correlation, that's guideline for the application of the multi-energy method, and that's used in softwares like FAST, and we compared that to CFD. And had there been a correlation between 2 methods, then all of these points would be sitting on the line. Obviously, they're not. The R squared for the 2, or R squared between the 2, was 0.3. By comparison, one of the PhD students out of UWA actually came up with a much better method. Again, it's an analytical estimate, but this is how it compares to CFD. And it's been compared over about 3,000, two sets of 1,500 cases. And you can see here, the R squared here was about 84%. And so this method is what is used for gas explosions as the source. Just load a drawing. This is a normal plot plan of an area. You could see it's picked up all the lines, and you could select and deselect the lines. So in this particular case, we have an explosion on an FPSO off the coast of this is in Brazil, actually, off the coast of Brazil, the south of Brazil, and you've obviously got some industrial facilities here, some important sort of storage tanks here. More importantly, here, a kilometer away, there is a sort of residential area, and so it's easy to select and deselect walls or lines to be treated as walls. So, for example, this line here demarcates the shoreline. You don't want that to be treated like a wall, so you can see you can easily deselect it, and it goes purple or gray in the software. And you set up the parameters, which is very easy to do for the gas explosion or the BLEVE or the TNT explosion. You set up the gas cloud, and when it's done, it outputs the shock wave, the explosion that's coming out from the vessel. Other examples we have here. This is a redo of Bunsfield. You could see the explosion on 3 Cherry Trees Lane coming out towards the buildings. And one thing that you notice about this is you could see the reflected shock wave. If you look over here, this is, you don't see this in normal or in other CFD softwares. You can see the reflected shock wave very clearly. Again, look over here. When the shock wave reaches the tank, you'll see the reflected pressure on the tank very clearly. And this is because we don't turn it into a porous medium or anything like that. You see that shock wave reflecting off the tank, very clear. So there's a high resolution capture. This is an ammonium nitrate explosion that's occurring on a site, and you could see it interacting with the walls, with the facilities as the explosion propagates. Obviously, the pressures are extremely high in the case of an ammonium nitrate explosion. All these are prior real cases for clients. This is a BLEVE in an industrial facility. This is a tank undergoing a BLEVE. I think, to my knowledge, okay, Xplo CFD is the only software in the world that actually models an ignition of a flashed flammable vapor on top of the BLEVE. So the BLEVE is actually the rupture of the tank, and there's a flash and an overpressure that's created. But on top of that, the released chemical may be ignited, and Xplo CFD is the only software that actually models that as well. It could make a very big difference in terms of overpressure. You could go from half a bar to 10 bar if the tank were in a congested area and releasing a high energy material. We've done a lot of validation on this. As I said, the components are heavily tested. CSC and the other analytical methods have been heavily tested. And also, we've been looking at the integration of all of these components together. So these are the BFET's repeatability tests, and you can see agreement here as the shock wave propagates outwards from the source of the explosion outwards. This is about as good agreement as you're going to get from any explosion modeling software, 2D, 3D, or any other type. The software performs as well as you might expect, and of course we continue to keep testing it and pushing its limits and seeing how far, where you can and where you can't use it. But it's very easy to use, and it's a quick, rapid solution, and that's one of the more attractive features that it has. It certainly beats the sort of concentric circles that you get with other analytical methods, where the walls, the obstacles, the other features of the geometry are not taken into effect, or some method that just interprets CFD results, or interpolates, CFD results. That's, you don't know where you're sitting as far as that, the accuracy of that is concerned. This is a method that interacts with changing problems, so you can adapt it to cases, geometries that you have never seen before, and that is a very important feature.
Catastrophe unfolding in the ISOM unit. As flammable hydrocarbons overfilled the blowdown drum, operators nearby saw a geyser of liquid and vapor erupt from the top of the stack. The equivalent of nearly a tanker truck full of hot gasoline fell to the ground and began forming a huge flammable vapor cloud. The vapor cloud expanded in just 90 seconds, engulfing the unit and the nearby trailers full of workers. About 25 feet from the base of the blowdown drum, 2 workers were parked in a pickup truck with the engine idling. As flammable vapor entered the air intake, the diesel engine began to race. The 2 workers fled, unable to shut off the engine. Moments later, witnesses saw the truck backfire and ignite the vapor cloud. Powerful explosions swept through the area. The blast pressure wave accelerated through the ISOM unit, causing heavy destruction and igniting fires. The workers inside the trailers were right in the path of the explosions. The fires continued to burn for hours. 12 of the 20 occupants of the double-wide trailer were killed, along with 3 workers in a trailer nearby. 180 workers were injured, many with serious burns, fractures, or other traumatic injuries. The wood and metal frame trailers were blown apart by the blasts. Firefighters struggled to rescue the injured and recover the victims. 50 large chemical storage tanks were damaged, and the ISOM unit remained shut down for more than 2 years. The disaster at BP Texas City was the most serious refinery accident ever investigated by the CSB.